Today, we'll be solving LeetCode 73. Set matrix zeros. We are given an m by n matrix of integers and the rule is simple: whenever an element is 0, we must set its entire row and its entire column to zeros. The twist is that we must do this in place, which means we cannot make a full copy of the matrix to write our answer into. So let's think about how to do this with minimal extra memory while keeping the code clear and easy to reason about. First, let's consider two straightforward ideas so we know the trade-offs. One idea is to make a full copy of the matrix, mark zeros on the copy, and then overwrite the original. That is simple but uses O of m times n extra space and is usually not allowed by the in-place requirement. A second idea is to scan once, collect the set of row indices that contain zeros and the set of column indices that contain zeros, and then do a second pass to zero out rows and columns. That uses O of m plus n extra space and is easy to implement, but it still uses extra space proportional to the number of rows and columns. What we want is an approach that keeps extra memory to a constant. The elegant in-place trick is to use the matrix itself as the storage for the markers. We will use the first row to mark which columns should become zeros, and we will use the first column to mark which rows should become zeros. Because the first row and the first column are being used as marker storage, we first need to remember whether the first row itself needs to be zeroed, and whether the first column itself needs to be zeroed. For those two original decisions we keep two Boolean flags. With those two flags plus the first row and first column serving as marker arrays, we can implement everything in place with only O of 1 extra space. Now let's walk through the code. First we check if the matrix is empty or if the matrix has no columns. If either is true, we simply return because there is nothing to do. Next we set rows to the length of matrix and calls to the length of matrix at 0 index, so we always know our dimensions. Then we create two booleans named first underscore row underscore 0 and first underscore call underscore 0 and set them to false to start. Next we check if the first row originally contains any 0. We do that by looping through every column index j from 0 up to calls -1, and for each column we check if the element at row 0 and column j is equal to 0. If we find such an element, we set first underscore row underscore 0 to true and stop that loop. Similarly, we check if the first column originally contains any 0 by looping through every row index I from 0 up to rows -1, and if any element at row I in column 0 equals 0 we set first underscore call underscore 0 to true and stop that loop. These two checks preserve the original state of the first row and first column before we overwrite them with marker information. After that we mark rows and columns using the rest of the matrix. We loop I from 1 up to rows -1 and for each I we loop j from 1 up to calls -1. For each cell at row I in column j, if that cell is equal to 0 then we set the cell at row I in column 0 equal to 0 and we set the cell at row 0 and column j equal to 0. In plain terms, if a cell in the body of the matrix is 0 then we write zeros into the first cell of its row and into the first cell of its column, and those become our markers. Once marking is complete, we use the first column markers to zero out rows. We loop I from 1 up to rows -1 and if the cell at row I in column 0 equals 0, then we loop j from 1 up to calls -1 and set each cell at row I in column j to 0. That zero's all the interior of that row because the marker told us this whole row must be 0. Then we use the first row markers in the same way. We loop j from 1 up to calls -1 and if the cell at row 0 and column j equals 0, then we loop I from 1 up to rows -1 and set each cell at row I and column j to 0. That zero's columns based on marker information. Finally we apply the flags we saved at the beginning. If first underscore row underscore 0 is true then we loop j from 0 up to calls -1 and set every element at row 0 and column j to 0. If first underscore call underscore 0 is true then we loop I from 0 up to rows -1 and set every element at row I and column 0 to 0. That finishes the in-place transformation. A few subtle but important why and how notes. We start marking from row 1 and column 1 and we only write markers into the first row and first column. We never overwrite the entire first row or first column until the very end, because those two rows hold our marker bits. That is the reason for the two Boolean flags. They remember whether the first row and first column themselves needed zeroing before we started writing markers into them. We check the first row and the first column up front and save that information. Using markers inside the existing matrix is an example of trading a small amount of logic for constant extra memory, which is a common pattern when the problem asks for in-place modification. Let's talk about complexity in plain language. The time complexity is O of m times n because we do a constant amount of work for each cell in the matrix across the scanning and marking passes. The extra space complexity is O of 1 because we only keep a couple of Boolean flags and reuse existing matrix cells for markers. If you were to use sets to store rows and columns, the time would remain O of m times n, but the extra space would be O of m plus n. Some edge cases to keep in mind as you implement and test. If the matrix has only a single row or only a single column, the logic still works because our loops gracefully handle those sizes if you respect the bounds. If the entire matrix is already all zeros, the code will correctly keep it all zeros. If there are no zeros, the code will also leave the matrix unchanged. If the matrix is empty, we return early. And that's how you solve LeetCode 73. Thank you for watching, and let's keep learning.